Thank you.
So Katharine, do you want to start sharing your screen? Next up, we have Katharine Shapcott, who is talking about rank similarity filters on computationally efficient machine learning on high-dimensional data.
Okay, I think this is working now.
Yeah,
Hi,
good.
I'm Katharine. I'm working in Frankfurt in Germany, and yes, I will talk about rank similarity filters. So that's a novel type of artificial neural network that's very efficient. You can check the preprint in the agenda if you're interested, and also the code is all on GitHub if you'd like to try it out. So yes, similarity judgments are something that the brain can do very intuitively. So all of us can hopefully do the following task. So if I show you what is probably a novel object for you that you've never seen before, you'll already be able to tell me how similar it is to other objects. So for example, this bike and this car, you can see in which ways it's similar and in which ways it's different. And this is what we call one-shot learning. So already, just by seeing this object once, still not really knowing what it is, you can already make these similarity judgments about it. So how might the brain do this? So I think this could have something to do with vector quantization. So this is a method of data compression. So instead of needing to store all the data of all the bikes and all the cars that you've ever seen, you can just store a few prototypes of the data. And these prototypes can then be used for classification because they contain information about similar data. So similar data gets grouped into one prototype. So for example, here, maybe these would be the bikes and these would be the cars, right? And the prototype bike could be this in the middle, prototype car. And your novel object here, because it's well outside the other groups of data, could be its own prototype, and you can already decide how similar or different it is to the other groups of data. And you can also see in a high dimensional space which features are similar and which are different for this. Okay, so this is the theory kind of, but how could neural networks do this? So actually it's very easy for them to do this. So right, a node in the neural network would be, it has weights, right? So the vector of weights, and these weights could be its location in the space. If you would then have inputs, the neuron that have weights that matches the data better. So in that case, the blue neuron here, it will have a larger response. The red neuron here would have a smaller response. And they could inhibit each other. And then this would be the prototype for this new data. And then the weights could update so that this would become the prototype of this class. And you could have as many prototypes as your network allows. But the problem with this is that firing rates are fluctuating all the time. And we're not mapping a stationary space as in the previous slide, but actually we know that the firing rates are changing constantly. So how can we handle this? So what we thought was that actually we might use the confusability of features. So this is a new measure. Basically, what it is that you have here, for example, this blue feature. This is very far away from all the other features, and it's very different between the classes. So this would be a feature that's not very confusable with the others, and it would be highly weighted. Whereas this green and yellow feature, they're much more similar to each other, much more likely to overlap, and then you give them less weight. But what you maintain is the ordering of the features. And especially when you get to very high dimensional data, which is what the brain is good at dealing with because each neuron tends to have tens of thousands of inputs, actually the specific values in this high dimensional space don't tend to be as meaningful anymore. whereas the order of the inputs are meaningful, even in very high dimensions. So this we maintain. So here you can see in a fashion MNIST dataset, which is commonly used, that was on the first slide, that the rank follows very nicely. When you have the, can someone turn off their mic? Then you see that the confusion is following the rank here. So in this case, for this data set, you don't even need to calculate the confusion. You can just use the order statistics, so the rank of the data, and this already works for weight setting. In another data set, 20 news groups, this is text data. This follows an exponential function. Here, the rank is no longer a very good approximation of this, and you do need the confusion to set the weights properly to deal with this data. So I decided to make an algorithm of this. So because it was such a simple idea, and it's very, very fast. So all you have to do is create this distribution of confusion if necessary. You initialize the neurons or the filters in the space. You spread them through the space based on this rule of the winner then takes the data and updates its weight accordingly, and then you normalize them. And then you have your prototypes already. And the spreading here is just done by a dot product of the neuron with the data and then the winning neurons or prototypes. They are the ones who then update using this rank of the mean of all of the points that they won. And you do this until the points don't change their prototypes anymore, which can sometimes just be as few as 5 iterations, maybe up to 20. And yeah, so it's extremely fast. So here would be an example prototype vector on the fashion MNIST dataset. And what you would do is multiply it with a new piece of data that comes in. So in this case, a sandal. You do the dot product, and this is the response. And so here are the winning prototypes in this case. And you see that they're all similar looking sandals. And you can use this to transform the data set. So here you see just some random example data fed in, and these would be the top responding filters. So again, because it's quite high dimensional, the absolute distances don't matter as much anymore. So we just keep the top responding ones and their relative responses and transform the space this way. And you can set all the rest to 0 because it's not meaningful anymore. So if we take a support vector machine and we apply this rank similarity transform to the data, so this is the raw score of the SVM, so it's linear, so it doesn't do so well in this data set. If we give just 26 of these prototypes, it's not very good. But as soon as we move to 150 of them, you can see that it's beating the raw SVM. And by the time you get to 1,500, it's really doing quite a lot better. And the really cool thing is it's also a lot faster. So with 1,500 of these prototypes, you see that it's still only taking 10 seconds. And this includes the time of the transform and the SVM running. So it really is quite a lot faster. And that's actually increasing the dimensionality of the data. The original data is only 784. So yeah, that's a pretty nice result. And actually you can directly use this as a classifier. So that's the rank similarity classifier. So here you see actually the performance is even better. And here we have the number of samples. So we're making the task. Here it's quite difficult. And already you see very good performance with just 1,000 samples or so. So this is also nice, and it's even faster again, because now we don't have the time of the SVM, but instead we use the labels of the prototypes to assign a class to the data. Yes, and we can compare this. There are some other classifiers that have been tested on this data set. And so the parameters, the best parameters that could be found with a parameter search on the fashion MNIST data set. And this is the rank similarity classifier here. So you see that it's not reaching the performance of, like, for example, an SVM with a radial basis function here, but it's really an order of magnitude faster. So that's like a huge difference in speed for quite a small performance gain. And this is after a parameter search, so it's even slower to find actually all of the correct parameters that you need to get such a good performance on a nonlinear data set. So yeah, that was it. So what I would like to do next is test the biological plausibility of this. So what I'm trying to do at the moment is implement the algorithm on neuromorphic hardware. And I would also like to try and use this as a weight setting method for a recurrent network, because it's so fast that this could be a very good starting point for then further training to take place. And I'll be doing recordings in monkeys in the Havnet and Scholfink lab in a very dynamic task where I should be able to see if we see this type of maintenance of ordering, because we'll have quite some number of channels during the task. Yeah, and I'd like to thank Alex Bird, who helped me a lot with this project. Yeah, and the entire Singer Lab and the Instrument Institute and the FIAS for support. Thank you.
Thank you. I shall clap on behalf of everyone. You stuck very nicely to time, so we do have time for a question while people may be composing their thoughts. Is there any reason why your approach wouldn't work for like sounds or multisensory stimuli? Or, I mean, obviously you've been doing visual images.
Yeah. No, I mean, it works on text data, for example, right? What it's not very good at, because it's using orders, if your features have no relation to each other whatsoever, then the ordering becomes meaningless. So this it cannot do. So I don't know, there's some data sets that, yeah, it just doesn't seem to understand them. I guess if you would get the correct scaling, because it's very rare that actually that the different features have nothing to do with each other. It's quite, you know, they're always somehow related. But yeah, if they're very highly unrelated, then it won't work at all. And the other thing, it's not good at low dimensional data. So you need enough dimensions to have enough ordering to actually get enough information out of this. But that in the current day and age is not really a problem. We have plenty of dimensions of our data.
Yeah. Well, and in the real world too, right? I mean, the real world has many dimensions. It doesn't look like there are any more questions, but again, people can follow up either here or in Discord later. Dory, I'm really pleased to see you're here. Oh, there is a question. Let's look at the question. While Dory maybe shares her screen. So would this algorithm handle translational invariance in images? That's from Carl Johnson.
No, so it's a single layer. So no, it can't handle that. That's another thing I would like to work on. If I can layer this, then it should be able to do that. But then I need to section the other layers, and I haven't found a good way to do that. But yeah, it's just because it's a single layer, it can't handle that.
Cool. Thank you again for a lovely